Hi everyone, this is Dr. Nigro with a notes screencast for our unit on electrostatics and Ohm's law. This set of notes will be broken up into several parts. You may watch the part that you need. You may go back and review all of the parts. It's kind of up to you. But it's going to follow along with the notes packet that I handed out in class or that is attached here. All right, if you have any questions, as always, please come ask me at school. All right, so our current unit is looking at electricity, and electricity comes down to charge, and that's where electrostatics come in. We're not going to do a lot with electrostatics. Electrostatics is just this idea that charges that are the same will repel each other and charges that are opposite will attract each other, and that leads to a lot of the phenomena that we see when it comes to matter and then electricity. We're going to focus more on Ohm's law, but before we can get to that, we got to start with where these charges come from, and that means we got to look back just a little bit at our friend, the atom. All right, so back in chemistry, we learned about the atom. We learned its general structure. We know that in the center of the atom is our nucleus, and this is where most of the mass of the atom resides. And that mass is wrapped up in two separate subatomic particles, our proton, all right, which is our P plus and is a +1 subatomic particle, and then our neutron, which is N0, which has 0 charge. All right, those two are the massive subatomic particles, and that's a very relative term. They're obviously tiny, all right, but compared to the third subatomic particle, which is zipping around outside of the nucleus, the electron, they are massive. All right, so the electron resides outside of the nucleus. All right, e to the -1, it has a -1 charge. All right, so these are three subatomic particles that make up the atom. All right, now we also learned in chemistry that if the protons equal the electrons, we have an atom, which is neutral. We learned that if the protons do not equal the electrons, then we have an ion, which is charged. All right, and when we have charged ions, they can interact with each other, or depending on the type of element, those electrons may jump from atom to atom. When they jump from atom to atom, we call that fluid electrical charge. That is where our electrical current comes from that we then use for all the stuff in our house. All right, so in chemistry, we would say that an ion is a +2 charge or it's a -3 charge, which was fine for what we were talking about. But in physics, we need to be a lot more specific. And an electron is not -1. It's actually a much smaller number than that. All right. So if we want to quantify this charge, all right, we need a formula for that. So charge is represented in our formulas by the letter Q. All right. Sometimes you might see it as a lowercase, but we've been using capital Q. All right. And that's going to be equal to this variable N and then a constant E. All right. So N is the number of balanced charged particles. All right. And then E is a constant. It's either plus or minus 1.6 times 10 to the -19th coulombs per particle. All right. Now, when we talk about particles and charge, once we move into electricity, it's all going to be about the electron. But for this one instance, if you're talking about having more protons in an atom than electrons, then your charge Q is going to be positive. So you use positive 1.6 times 10 to the -19th. If you're talking about having more electrons than protons in your ion, then you're going to have a negative charge, and you have negative 1.6 times 10 to the -19th. But once we get into electricity, then it's all going to be the electron. All right, so the unit for charge here is a new one for us. It's the coulomb, and it's abbreviated with the capital C. All right, so let's try a quick problem. What is the total charge in an ion with 10 electrons, 7 protons, and 7 neutrons? All right, so here we have more electrons than we have protons, and we have 3 more. All right, now if we were in chemistry, we'd say this is a -3 ion. All right, but in physics, we're going to calculate what that value actually is. So we say Q is N times E. All right, so Q is going to be 3 electrons times -1.6 times 10 to the -19th coulombs per electron. All right, and so what we find is instead of a -3 ion, we actually have an ion that has an actual charge of 4.8 times 10 to the -19th coulombs, and that would be negative because we have excess electrons. All right, so you can see that's a lot different than -3. All right, all right. So now let's talk about what we can do with these atoms. So atoms fall into 3 different categories in general. We have our metals, we have our nonmetals, and our semimetals. All right. The metals are a conductor. So what is a conductor? It's a material that allows electrons to flow through. All right. So in other words, they hold their electrons loosely. They're willing to donate them to other atoms. So the electrons within these atoms are mobile. All right. They don't require a lot of energy to move them. All right. So the examples of materials, these are going to be our metals. All right. Now there's a wide range of the ability to be a conductor. Some metals are really good at it. Other metals are good, but not as good at it. All right. But in general, metals are conductors. All right, an insulator is the opposite. It's a material that blocks or slows the flow of electricity. All right, and these are going to be your nonmetals. All right, things like carbon, nitrogen, oxygen, phosphorus. All right, these are atoms that hold their electrons very tightly, so they don't let them move around too much, and they are not willing to part with any. So we don't have any electron motion because they hold them so tightly. All right, now our semi-metals aren't on here, but those would be our semiconductors. They can sometimes be conductive and sometimes not, depending on the environmental conditions. All right, why do most electrical wires have both types of materials present? Well, generally it's for safety and efficiency. All right. The safety part, we basically want the electrons to stay in the path of our choosing. All right, so if we set up a wire and we want electricity to move from point A to point B, we want it to move from point A to point B. We don't want it to be sparking off to the sides and zapping things that might be around that wire. So to help with that, we wrap the wire in something that is non-conductive, like rubber, and that keeps all of those electrons in that path that we have chosen. All right, so you're most often going to see wires that are wrapped. All right, the only time that you'll see unwrapped wires are at the very ends where we've got a metal to metal contact so that the electricity can be conducted to somewhere else. All right, now dictating all of this flow of electricity is another law, and that's the law of conservation of charge. And just like our conservation of mass and energy, conservation of charge means that charge cannot be created or destroyed. All right, destroyed. Only transferred. All right, so that's a little bit different, the word transferred. Or with energy, we always say it can be transformed. With matter, we can say it can be transformed. But for charge, you're not transforming an electron to anything else, but you can transfer it. You can move it from one place to another. The key is that the total charge you had to begin with has to be there at the end. You can't pick up any additional charge, and you can't destroy any of the charge that you have. All right, so it's really similar to other laws. All right, now the movement of charge is going to be based on 2 factors, attraction and repulsion. All right, negative charges are going to move towards positive charges, and negative charges are going to move away from other negative charges. All right, so here we have an example. We have a sweater that has a big buildup of positive charge. And then over here, we have a balloon that has a big buildup of negative charge. And the question is, which direction will the balloon move? All right, well, positive and negative attract. So the balloon probably is going to fly over and attach itself to the surface of that sweater. All right, so just remember, electrons repel electrons and protons attract electrons. And that's really, at its base, is what electrostatics is all about. Okay? So that's just our first look at charge, how to calculate charge, where it's coming from, all right? And this idea that it has to be conserved. Okay? Tune in for the next screencast. That one's going to look at current.